All right, thanks you guys. Thanks for waiting. So today we're going to be talking about how to solve problems in Mathcad Prime. There's a few ways to do this. There's built-in worksheet functions, which are very useful. We also have symbolic calculations, which are great as they can provide insight into relationships between variables. Another thing that I really like is solve blocks. You can solve systems of linear, nonlinear equations, even systems of ordinary differential equations. And with all these processes and these functions available, we're going to explore and compare them and see just a little taste of the problem-solving capabilities within PTC's Mathcad. So these are some use cases of the problem-solving tools in Mathcad. We can find solutions for a variable in an equation using symbolic calculations or built-in Mathcad functions. We can also find solutions for multiple variables in a system of linear or nonlinear equations, solving this symbolically or using a solve block. Optimization problems are very handy to do within Mathcad. We have solve blocks that can handle them very well, and also built-in Mathcad functions if you just want a quick and easy way to do it. We'll also be solving a spring damp system, so you'll get a taste of how to solve an ODE within Mathcad using a solve block. On the right-hand side, you can see an example of an engineering problem. This one is specifically trying to find a lambda in a pressure seal equation, And so as you notice, we have some complex values there in the solution and some real ones, and we'll dive into this and more symbolic calculations a little bit later in the presentation. So first thing we'll talk about is the built-in functions within Mathcad used to solve. So on the left-hand side, you can see we have 8 functions here. We have find, lsolve, maximize, min-err, minimize, ODE solve, polyroots, and root. Some of these can only be used in solve blocks, the ones with a red box around them. The ones with a blue box can only be used in a worksheet, and the green box ones can be used in either solve blocks or a worksheet. So just to go over the worksheet functions, there's 3 worksheet functions for solving equations in Mathcad. We have root, which can provide roots of a function f, and then you have to provide it a guess value for the variables that you are using in that function. And optionally, you can also specify a solution range where a would be like a negative number and b would be a positive one, and within that range, it'll look for a solution for your function. We also have polyroots, and this takes a vector input. So with the vector input, your first term is going to be your constant term. Your second term would be the coefficient that corresponds to, say, x. The third term would be a coefficient that corresponds to x squared, and so on. So this is very useful at solving polynomial equations. It will provide you with all the roots for that polynomial equation. And last, for our worksheet functions, we have lsolve, which solves a system of linear equations. You provided a matrix of coefficients and then a vector of the solutions for each equation. And from there, it can just spit out the values of your first and second or third variable, however many variables that you need to solve for that system of equations. So to see these in action, let's take a look at our worksheet here. So these are the worksheet functions we have. We've defined this function p of t, where we have t cubed minus 15t plus 5, and we have t as our guess value here at 1. So we just want to find the root of this function with one variable t. So as you can see, we're going to just select all of the stuff in the inputs, and we're going to put our own inputs here. So we're going to put p of t as our function, and then we're going to define our guess value as that t we previously defined. And Mathcad calculates it, and we get a root of 0.336. So if we were to put this value back into this equation, we should get a 0 out for our function p of t. Likewise, we're going to show how polyroots can do something very similar to this. So we have our vector v here, and if you look at it, we can see that it's the exact same function or equation previously defined, where we have 5 as our constant term. We have negative 15 attached to our t variable. We don't have a t squared, and we do have 1 t cubed. So within polyroots, we're just going to set it to solve the vector v. And as you can see, we get 3 roots. We get negative 4.03, the 0.336 that we got from our root solve function, and then we get one more root, which is a 3.694. So polyroots is great for solving polynomials. It can handle a lot of stuff and make your make your work a lot easier. If you do have a system of linear equations, we would solve it using LSolve in the worksheet. So our M matrix is our coefficients where we have 4x minus 2y, and then our second equation is pi x plus y. The solution for our first equation would be 8, and the solution for our second would be 7. If we're just to plug these in here, we can see we get an answer out of 2.139 for our x value and 0.297 for our y value. So if you're wondering how you actually get these functions into your worksheet, you can either type them, and when you add that parentheses, Mathcad kind of knows that you're typing a function here. It'll check its built-in functions. If you forget about that, or if for some reason you're typing it in and it's not showing up, you can always go into this functions tab and then just click on whatever function you'd like to add in. All right, so let's get back into our presentation, and we're going to take a look at symbolics next. So symbolics are awesome. You have a lot of benefits. You can evaluate expressions without actually having values attached to the variables. This helps you kind of get insight into the behavior of those variables and their relationships together. And because you're solving most of the symbolic calculations without values, you're immune to round off errors. It will try and provide you with an exact solution if possible. There are a lot of different keywords and modifiers that you can use with symbolics, as you see on the left-hand side. We'll be going into a few of them today. We'll be talking about simplifying, expanding, factoring. We'll also be showing you how to get a decimal result instead of a fractional one from your symbolic calculations. We'll also be talking about inverse Laplace, how to solve an equation for x fully, which is a little bit different than just solving for it. And we'll also be showing you how to solve a system for two different variables. So let's get back into our worksheet and we'll take a look at symbolics. So the first thing we're going to do is simplify here. So to add a symbolic, you can go into this symbolics tab under the math and just click this arrow here. By default, symbolic will simplify your equation. So if you do type simplify here, there's not going to be any difference. So that's just something to understand when you're working with symbolics. It might save you some time instead of having to type out simplify. If we do want to expand that, we would have to write it in there. And if you notice, I did add the arrow pretty quickly. I hit Control and the greater than sign, and that inputs an arrow for you. If as you have more experience with symbolics and these calculations, the shortcuts should become apparent to you. If you guys are interested in learning about shortcuts, let us know, and maybe we can do a video on those. And here we're going to factor this result. So as you can see, Mathcad is able to do a lot of these manipulations that may take you a lot of time on paper. I know expansion might take a few minutes to do sometimes, depending on how many times you're multiplying it out. So this is a great way to kind of skip a lot of steps and just do things a little bit easier. If you want to evaluate integrals, likewise, we just add an arrow here, and by default, symbolics will solve this for you. In this integral, we actually have values here, so it's going to give us fractional results. But say, for example, I do want a decimal answer. I can type float and then specify the decimal places I would like to float to, and it will provide me with a numeric results. This numeric result can actually be used further on in your calculations, as we'll see in this next problem. So that if you recognize this from the presentation, this is one of the problems we talked about earlier. You can see we've already solved for lambda, but in this case, I don't want the complex solutions here. So I'm just gonna add another line here by hitting Shift Enter, and then I'm gonna assume that our lambda is going to be real. From there, it just isolates the real solutions to this problem. Instead of hitting Shift Enter to make a line here, you can also do a comma. They're equivalent. So if you're running out of room horizontally, I like to use a Shift Enter instead of a comma, but either one would work for you in this situation. Here we're going to get the full solution to an equation. So we have this equation laid out here, 3yy times xx minus 3 equals to 10. And we want to solve this for xx. And as you can see, we do get a solution here, but if yy is 0, then this is undefined. So in that case, let's say we want to solve this fully. When we solve it fully, Mathcad is able to provide us with a programmatic solution where we have conditionals. If yy is equal to 0, then it's undefined. Otherwise, if yy is greater than or less than 0, we have our initial solution where 9yy plus 10 over 3yy. So this is very handy in some situations where you're going to test all the values of yy against and get results for xx. You want to have a fully solved solution, fully solved equation here instead of just one with undefined points. Our last symbolic example is how to solve a transfer function. We have our transfer function defined here as t of s over s squared plus 2s plus 3. This is our t vector, time vector, goes from 0 to 20, and we have 0.1 steps in between. So to solve this, we're going to do the inverse Laplace. And if you notice, right now, all I did was add the delta t in there, but we need to specify that we want to do it with the variable s. So I did put s in here, and you notice that it still hasn't really updated anything. So something inherent within symbolics is if you use a variable that's not defined previously, like this s, it's going to assume that it's a unit, as we see up in the label here. We need to actually specify that it's a variable. And once we do that, then we get our results of the inverse Laplace. And as you can see, we have it plotted here, r of t across this t vector. So that's the last of our symbolics, and we're going to get back into our presentation and go over solve blocks. So solve blocks are great. You can use guess values, and what it will do, it'll step towards a solution iteratively. It'll get closer and closer until it converges on a solution for the constraints and guess values you've provided. You can use this to solve systems of linear or nonlinear equations, also systems of differential equations. So these are the functions that you can use within a solve block. We have a find function, which when placed in the solver section of our solve block, it will return the values for each variable that you provide to that find function. If for some reason find cannot converge on a solution, if there's an error and you want to troubleshoot that and maybe find a better guess value for those variables, you can use min error at the bottom there. And that runs through the same process that find does, but it will return a value of the minimal error between the variables it's trying and then the solution that you would like to get as defined in your constraints. As you see later, this will become more apparent to you guys. Also, we have maximize, which is used for optimization, where if you provide a function f and then the variables that are inputs into that function, it will try and get the highest value for f, and it'll spit out the variables that provide that value for f. Likewise, minimize does the same thing, but in reverse, it'll find the most minimum value for f, and it'll spit out the variables that provide that minimal value for f. If you do have ordinary differential equations, you can solve them using ODE solve. You can either use one function, as in x of t, for your first input here in ODE solve, or you can provide a whole vector. Say you want to get x of t and y of t, then you'll be able to provide a vector of functions. Also, you need to have an endpoint. So this is how far you're planning on using this ODE. And also solution points are optional by default. You have a 1,000th point precision, but you can specify different precision based on if you need a higher points or maybe you need less. You have the ability to change that. So without further ado, let's get back into our worksheet. Here we have our first solve block. You may notice this clear here on the side. So what that does is it actually clears any x or y variables previously defined. So without this clear, this x and y would actually have a result. Since I'm using the same variables, I'm just going to put clear here, and then we should be good to go. So we do have our guess values defined here. In order to define a guess value, you need to use the definition equal sign. So that can be done by just typing a colon in your worksheet, or if you're unfamiliar, we can always add it in through our operators tab here, definition. For constraints, we have our constraints laid out as x minus pi y equals 6. And this is actually a comparison equal sign, which you can enter by hitting control equals, and it gives you like a bolded equal sign. Usually this is used in validating like a binary truth. If they're the same, it'll spit out a 1. If the two values on either side of this equal sign are false, it'll spit 0 out. But in solve blocks, it behaves a little bit differently. This is how a solve block knows that you're providing constraints. Without using this comparator equal sign, as seen here, then your solve block will not function as you would like it to. So once we have our guess values defined and our constraints defined, we can add something in for the solver. So a solver also uses the definition equal sign here, but the way that it can tell that it's a solver and not a guess value is when you enter a function here. So we'll do find, and we just want to find x and y. So after typing find here and x and y, you can see the solve block intuitively separated the values we have. So we have guess values assigned to these, and we have our constraints here. And then the solver is our definition equal sign attached to one of those solve block solve functions. So after we find x and y, it just spits it out here on the right-hand side. X and y equal 12 and 1.91 respectively. You can solve the same equation using symbolics. I've also cleared symbolic variables, so there's two different procedures. There's one for local variables, and then there's another for symbolic variables. So just something to keep in mind if you're getting weird results when you're trying to solve some equations. So to solve this, I'll do solve, and I would like to solve for x and y. And then we have this solution here, which is, it keeps your variable letters. So there's no values assigned to this. You get to see the behavior of all the coefficients and variables in your equation without actually getting a real result out. So this is especially useful if you're doing a lot of hand calcs, and this may save you some time for sure. If you're solving systems of nonlinear equations, this can be kind of difficult sometimes. So solve blocks make this a lot easier. So likewise, we can just type in this find and then a and b. And since we have our guess values here, a is equal to 1, b is equal to 1, and then we have our constraints, the solve block's able to spit out a and b, where a is equal to 1.462 and b is equal to 1.537. So nonlinear equations are not very hard to handle for Mathcad, especially in the solve blocks. Likewise, we can do it in symbolics again. In this case, we'll solve for a and b. As you can see, we get all the solutions, not just the one closest to our guess value. So if you are interested in seeing the solutions for the whole system of linear equations and not just the ones close to your guess value, I'd recommend using symbolics. And like we saw previously, where you can assume that something is real or complex, you can always sort your answers out by adding some assumptions into your symbolic calculations. All right, optimization. These are some of my favorite problems. So in this equation, in this problem, we're going to be trying to minimize the surface area of this bag. So we have a paper bag. Our base is width times the length. The sides are the 2 times width and height, and then the front and back are the length times the height. So this is the full surface area of our bag. We've defined it outside of the solve block. We've provided some guess values for length, width, and height. We know that we want our surface area or our volume to be 1.5 feet cubed, and we don't want any of our values to be less than 0. So we're defining all these constraints here. In order to solve this, we're going to use minimize, and we're going to provide the function SA, and then we're going to provide our 3 variables, L, W, and H. And from there, Mathcad just solves it for you. We get our surface area minimized at 6.24 feet squared, and then these are the length, width, and height values for our paper bag. As you can see, they're not really close to our guess values, so is some room for error in guessing a value. So this is very handy to do if you have some kind of equation here. It doesn't have to be surface area, it can be pretty much anything, and you want to minimize that and you have the right guess values and constraints, then a solve block can take that away and make your life a little bit easier. If you don't have constraints, we can still do optimization. So in this case, we're just going to maximize this function, and we're going to have f as our function and then u and v. And here we go, we get our solution out real quick. Our maximum f is going to be 1.091, and coincidentally our u is also 1.091, and our v is equal to 0.182. So likewise, these aren't really close to our guess values, but Mathcad's smart enough to find the solutions that make this the largest that it can be. You can also perform these minimize and maximize functions within the worksheet without a solve block. It's kind of nice to do if you don't want to have the whole solve block setup going. So to do this, we're just going to provide our function f, and then we have our x and y defined here with guess values on the left-hand side, where our guess value for x is 1 and our guess value for y is 1. From there, we just let it do its thing, and we've minimized our solution of f, which gives us a 4.429. And then we have our x value is negative 1.714, and our y value is 0.429. Something to take into consideration when doing these optimization problems, a constrained optimization may be harder to do in a worksheet. So if you're going to do constrained, I would definitely recommend using a solve block. Unconstrained ones are pretty straightforward. You can do them in a worksheet very easily. And our last solve block examples, we're going to be solving an ordinary differential equation. This ODE is a mass spring dampened system. We have our force pushing the system as 1 over 2 cosine 3 pi over 2t. We have a mass defined as 2. Our spring constant is k, and our damping coefficient is 2. So we have our equation set up here where we have mass times the second derivative of x with respect to t, plus our damping coefficient times the first derivative of x of t, and then our spring constant times x of t. And then this is all equal to our force function, which we've defined as f of t. We also know that our x of 0 is equal to 1, and our x prime of 0 is equal to 0. So in order to find our value, our function for x, we're going to type ODE solve, and then we're going to provide the function x of t. And then our stopping point is going to be 20. And like that, Mathcad's able to provide the function x of t, and we've graphed it here. You may notice there's no t value over here, and that's because we're using the same one from earlier, the 0 to 20 with a 0.1 step in between. So in that case, we can just use the same x vector here. And you can see that Mathcad relatively easily provided the solution to this ODE solve. And that's what we got for our solve blocks. Getting back into our presentation here. In conclusion, there's a lot of ways to solve problems in PTC Mathcad Prime 5. You can use the worksheet functions we have to solve roots or solve a system of linear equation. You can use symbolic calculations to evaluate expressions, and you don't have to assign values to those variables. You can get some valuable insight into the relationships between the variables that might not be apparent just from looking at the numerical results. Solve blocks are also really great at finding solutions to systems of linear and nonlinear equations, differential equations, and even optimizing solutions. So if you guys have any questions, feel free to ask away. Yeah, hope you guys enjoyed the demo so far.
Thank you, Trevor. Appreciate it. I hope that was very informative to everybody. There are a few questions that came in. One is a follow-up question, actually. So I'm just going to take us a couple minutes going through some of these. So remember we talked about when it comes to the copying from Mathcad to Word, the question is that when you bring it into Word, it's kind of in a bunch of different items. Is there a way to group them together?
No, you have to, Yeah, you'd have to like copy them into there and then group them into Word. So Word does have a grouping function, but you're not able to like select a whole section of your document and just paste it in there. Um, not with a copy paste functionality.
Okay, so that's something that this individual would do in Word. You would highlight them all, push like the control button and highlight them all and right click and hit the grouping.
Yeah,
Okay.
that's the best way I found to do it.
Okay, cool. James, I hope that answers your question. Feel free to follow up if you have anything else you'd like us to address there. Let's see. John has a question about the future of drop-down list boxes currently available in 15. John, I think we may have to follow up with that afterward, unless Trevor, there's anything you want to comment. I mean, that's with Mathcad 15. I don't know if you want to comment on that right now.
I don't really have anything to add for that right now.
Okay. So, and any of these questions that we can't answer right now, we will follow up individually or in a mass email with the question and the answers. Jonathan, thanks for the comments. Really appreciate it. Glad that you find this webinar valuable. Hope you can use the recording as well. An individual asked if we're going to provide the worksheets as an example. I think we can do that just fine. So Joe, let's make a note to just provide that worksheet that Trevor created and send that out afterward to all the attendees.
Yeah, no problem. Be sure to include that in the send out as well.
And Mark, regarding your question about using styles in Mathcad 15, Trevor, do you know, are you familiar with this feature of styles and whether or not it's included in Mathcad Prime?
I haven't used 15 too much, so I'm not too familiar about the styles, but I can definitely look into that for you guys.
Okay, we'll follow up. Mike Lockwood, thank you very much. Appreciate you joining us. Great to see you as always. Kuros followed up on his question about drawing. Can we add sketches? So let's say that he brings in a picture into Mathcad and then wants to add arrows and dimensions and other annotations. Do you know of a way to do this currently in Mathcad Prime?
No, I haven't seen any way to add arrows or anything on top of a picture. All we have is like the text box where I could just show you. We could add like a text box or something, but there's not really a way to add like arrows otherwise. I mean, you could do something like this. I mean, it's not really great, but that's the functionality we have in Mathcad for like adding arrows or symbols.
Yeah, Kuros, that's a great feature request. We'll make sure that the development team at PTC is aware of that. I guess one workaround is to just bring the data into Word, because Word has a lot of great, arrows and annotation functionality. But then, of course, you're working that in Word and not in Mathcad. So yes, the slides will be provided. Will there be features added to allow us to? Okay, the custom keyboards, will follow up on that, James, as well. Great. I think that answers all the questions. Please, if anybody else has a burning question you'd like to ask, we'll stick around for another 20 seconds or so. I don't see anything coming up. Oh, here's one. In general, many of the PTC examples have nice diagrams showing force and things of that nature, like a beam deflection diagram. But what is the general way to create these diagrams for Mathcad if you want to create a custom one?
Like a chart? Is that what?
So a diagram, and the example that Mike mentioned is kind of a beam deflection diagram. Is there a way to create our own?
Okay, like an actual CAD, like beam deflecting type of thing.
I
Like a,
believe that's what, and Mike, if you want to add a more detailed explanation of exactly what you're looking for, we can follow up with that as well. So everybody who's on the line, you will receive an email with the recording as well as a list of questions and answers. We'll just basically put them all in one email. So Jamal says that the header and footer settings are very limited in Prime compared to Mathcad 15 is what I assume the comment is. Is there a way, Trevor, to increase those or?
yeah, they're pretty limited. You can add things like the name of the file I have here and like a date. You can also add a page number. So this is your header and footer section, but they are pretty limited. You can't add any like components into it. So it is that's what we got for Mathcad Prime.
Okay. Oh, and Mike did just send a link. Okay, Mike, we'll follow up on that afterward. Thank you for providing that link. We'll include that as well. Okay, guys, I think we're good. Thank you all very much for your patience with us early on. Really apologize for the technical issues that we had, but we look forward to following up with all of you, and we're really glad to see the level of interest within the Mathcad community for these webinars. Our goal is to do a webinar every month, and based on the demand, we may increase that frequency as well. So feel free to reach out to us. You have our contact information. Please subscribe to our YouTube channel. All of these webinars will go on there, and you'll be able to see previous webinars as well. Thank you all very much, and enjoy the rest of your Thursday.